Hello and good afternoon or good evening. I'm going to just show a quick video to get you started on Lab 2. Okay, this one, again, just like the other labs, you will access the lab instructions from OpenIntro. And so these are the instructions, and so we'll follow along. And so here we're just going to kind of play around with a data set inside R and see kind of how we can manipulate and subset and do different things here. Okay, so here it says the first step in that process is to summarize and describe raw information, and we will look at data collected by the CDC. It's a large data set, and we will just kind of do a little bit of data processing here. Here we're going to look at the Behavioral Risk Factor Surveillance System, which is an annual survey with about 350,000 people. And we're going to look at kind of just different risk factors. And to get this loaded, we're going to just take a look at 20,000 people from the survey conducted in the year 2000. So it's already it's already starting to get old, but we're going to take a look at that. Okay, so to load this, we're going to run source, and it's going to be www.openintro.org/stat/data/cdc.r. Okay, so I will go ahead and start we'll have an R Markdown document here, but actually for this in the beginning we'll just deal with this blank script. So again, I created just a new R script, okay, and this is coming from openintro.org/stat/data/cdc.r. Okay, so I get that loaded up. Going to take a couple seconds to download from the internet. And so we will wait, and when it's done, we should see something that says a data set with 20,000 observations, but we'll allow it to take its time. Okay, and let's just kind of take a look at the next thing, and it should say that it shows up as a data matrix or a data frame, and we can look at the names of the variables that exist in our data set. Okay, so it finished loading, and so the next thing we're going to do is we want to know what are the names of the observations, or names of the variables here. So I say names CDC, and it has things like general health, XRNE, so like any exercise, health plan, so it's got these different things here. Okay, and so it says each one of these variables correspond to a question that was asked in the survey. So general health, respondents were asked to evaluate their general health, either excellent, very good, good, fair, or poor. The X or NE indicates whether the respondent exercised in the past month or did not. Likewise, health plan indicates whether the respondent had some form of health coverage or not. Smoke 100 is whether they smoked at least 100 cigarettes in their lifetime, and height in inches, weight in pounds, along with their desired weight, age in years, and gender. It says, so exercise 1 says, how many cases are there in this data set? How many variables? For each variable, identify its data type. Okay, and so we can kind of take a look at some of these data entries. So we would just do something like head CDC, and this is kind of the first few, and so we can see this is a general health as a categorical variable, telling us exercise any is also going to be categorical, but they're coded as zeros and ones. Same with health plan and smoke 100. These are all categorical, where yes is going to be a kind of a 1 and 0 will be no. And we can see these ones are numeric, and gender, of course, is categorical here. And it says we can look at the first few and the last few by typing in tail. So if I type in tail CDC, Okay, we can see you know, the entries 19,995 through entry 20,000. Okay, and we have it, and it says right here we've got 20,000 observations of 9 variables. Okay, and we can look at all of the data frame at once by typing its name into the console, but that's going to be unwise because this has 20,000 rows, and so it's going to just kind of flood the entire screen. So usually head and tail is much better. The survey has a lot of information, and we might want to just summarize some of this. So for weight, we can summarize the weight by doing summary $CDC $weight. Okay, so again, if we ask what are the names of CDC, we can see that weight is one of the variables, and if we want to access just that one variable inside the table CDC, I would say CDC $weight. Okay, and if I hit enter here, what it would do is it would just take this column of weight, of which the first one is 175, the second one's 125, and then the last 3 are 216, 165, and 170. It would print out all 20,000 different weight values that appear here. Okay, so I would hit CDC $weight, and I would hit enter, and you're going to just see a whole bunch of stuff fly up on the screen. Okay, and it says actually we just printed the first 1,000 entries, so this is the first 1,000 entries of what's in the weight, and it says, you know what, we omitted 19,000 entries. R recognizes that, man, there is a lot of information, so we don't want to do that. But we can do things like summary CDC $weight, and R has this function that will take all 20,000 entries and calculate some summary statistics for us. Things like, what is the mean? The mean of all 20,000 entries is just under 170 pounds. Okay, the largest value we observed is 500, the smallest value is 68, the first quartile is 140, and the third quartile is 190, with a median of 165. Okay, and so these are all the different weights that we have seen, and we can also, if we wanted some of these individually, we can run these commands, things like mean, variance, median. So I could just say, what is the mean of CDC $weight? What is the variance of CDC $weight? Variance is like the standard deviation, except it is the square of the standard deviation, or technically the standard deviation is the square root of the variance. So we can see that, you know, we have just over 1,600 and just over 40 for the standard deviation, which makes sense. And the median of CDC $weight is also given right here. And we can see that these values in summary match exactly what we would have gotten, right? So the mean in summary says 169.7, and the mean, if we typed in mean CDC $weight, gives us something very, very similar. Same thing with the median. We got 165, and indeed the median is 165 if we called this out. So that's what we do for numeric variables like weight or height, or what were the other variables? Names of the variables in CDC. Things like age was also going to be numeric and desired weight. Okay. Other things that are categorical, we can summarize using a frequency table. So we have table, and this will create a frequency table for us. So I can say table, make a table for the variable CDC smoke 100. So this is going to take that variable smoke 100 and make a table for us, and it says, you know what, we see the 0, we saw no basically 10,559 times, and we saw the value 1 9,441 times. So this is a categorical variable being summarized with a frequency table. Now if we want to turn it into a relative frequency table, we can say, okay, well, how many rows are there? There's 20,000 rows. So I would do this table, and I would just divide these numbers by 20,000, and basically I get about 53% versus 47%. So about 53% of people have not smoked 100 cigarettes in their life, whereas about 47% have in total. If we'd like, we can make a bar plot. So basically we just take that frequency table and turn it into a bar plot, which is exactly how we would make a bar plot if we were to do it manually ourselves. And so I would take, I'm going to just hit up twice on the keyboard to get back my command that says table, and I'm going to just write bar plot parentheses and close parentheses. I put bar plot table CDC $smoke. So table CDC $smoke 100 creates this frequency table, and bar plot will take this output and make a plot out of it. Okay, and so this is what the resulting bar plot looks like. It's a little wide that we have there, but here's 0, and as we can see it's a little bit taller than the 1. You know, it doesn't say this in the thing, but I like to have titles for my bar plots. So you would do something like main, and meaning main title, and this would be bar plot of people who have smoked 100 cigarettes. 1 equals yes. All right, now maybe this is, my title is too long. Okay, so bar plot of people who have smoked 100 cigarettes where 1 equals yes, something like that. Okay, we'll go back. Okay, the instructions say that basically we could have taken the table and stored it into an object called smoke and then called bar plot on that object smoke. These two things would produce the exact same results. So again, if I said table on CDC smoke 100, it produces this table. I could say, you know what, let's take table CDC 100 smoke, and then this thing, whoops, this is kind of the less than sign with a dash. You have to put them right next to each other. This means take whatever this outputs and store it into smoke. And when you hit enter, it doesn't look like anything has happened, but we can see that smoke now appears inside our environment. And if I type in smoke, we get the table back. Okay, and then I can call bar plot on this object smoke, and it produces the same plot that we had before. Alright, so it says create a numeric summary for height and age and compute the interquartile ranges for each. So that's easy. We would just do summary, and we would do CDC $height. Okay, we have our first quartile is 64, and our third quartile is 70, so our interquartile range would be 70 minus 64, and we would get 6. Okay, if we did it for age, CDC $age, the third quartile is 57 and the first quartile is 31, so we would get a IQR of 57 minus 31, or IQR of 26. Okay, and we can do compute the relative frequency distribution for gender and exercise any. So this is easy. We just do table, and we do CDC $gender. Okay, we have 9,569 males, 10,431 females. And I just change this, and we'll say, okay, well, almost 15,000 people have exercised in the last month, and that means about 5,000 people have not exercised in the last month. Okay, we also have the ability to create two-way tables. So we can, so far these have all been one-way frequency tables, or just frequency tables of one variable. If we combine two numeric variables, we will get a two-way table. So here we're going to look at gender and smoke 100, and I would just do table CDC $gender, comma CDC $smoke 100. And here it says of the males, 4,547 have not smoked 100 cigarettes, while 5,000 have, and of the females, 6,012 have not smoked 100 cigarettes, and 4,419 have. And so this is a two-way frequency table. And again, if we wanted to turn these into percentages, we can just divide this by 20,000. Okay, and that's kind of the overall percentage. Here we can also take this table, and throw it into what we call a mosaic plot. And let's take a look here. This is not a plot that we covered in class, but I think it's easy to understand. The width of the bars represent how many males and females total, and we can see that the female bar is just ever so slightly wider than the width of the male bar, indicating that there are more females than males. And then when we look at the vertical bar, we can see that as far as the males go, this is the number of people who have not smoked, and this is the number of people who have, and number of females who have not smoked, and number of females who have smoked. And we can see that because these bars are not, the breaks are not at the exact same location, these two variables are not independent. That as far as the males go, more people have said they've smoked 100 cigarettes, and as far as the females go, fewer have smoked a total of 100 cigarettes. And so that's what we have here. Okay. Let me see. If we had something, I don't know if any of these are truly independent. Oops, not names of CDC. Let's see. Maybe I can create a table of CDC $ exercise any, and well, let's do health plan and CDC $ gender. Maybe there's a relationship here. I can't tell. It seems like fewer men also have the health plan. Okay, so here we can see as far as health plan goes, a lot more people. This bar is way wider than this one, so there's a lot more that do have a health plan. And then as far as males and females go, the break is a little bit different, okay, but similar. So if I list the variables in the opposite direction, gender, comma, CDC $ health plan, then we see, whoops, we see it here. Okay, and so we can see again, the one is much bigger, and males and females, they're almost the same width, but the female width is a little bit wider, and we can see the proportions are very similar, but they're not exactly perfectly lined up. If they were perfectly lined up, then that would indicate the variables are independent. They're not perfectly lined up, so they're not perfectly independent, but that's what we have. Okay, let's see. All right, so here it says how R thinks about data, and it says R stores data in DataFrames, which we can think of as a spreadsheet, and we can ask, what are the dimensions of CDC, and this will tell you how many rows and how many columns it has. So if I say dimensions CDC, 20,000 rows, 9 columns is what it says. And here we can kind of give it coordinates, and if I do use square brackets, CDC square bracket, this will say go to the 576th row, or 567th row, it doesn't really matter, but 567th row and 6th column, and the value there is 160. If we kind of do head CDC, okay, we can see that 1, 2, 3, 4, 5, 6, the 6th column is weight, okay, and so if I wanted to get this value 125, I would do CDC square bracket 2 to say I want the second row and the 6th column, okay, and that would pull out the value 125, right? if I want to get this value right here that says 42, I would do CDC, and that's in the 4th row, and age is 1, 2, 3, 4, 5, 6, 7, the 8th column for age, and that would pull out the number 42. So we can kind of extract any value inside the table that we want. If you leave something blank, so if I do CDC 4, comma, it would just pull out the entire 4th row. So CDC 4, comma would pull out the entire 4th row, which we can see matches good. 110, 66, 132, 124, 42, so on and so forth. And if I did just the opposite, blank, comma, 8, this would pull out the entire 8th column, which would be all of the ages. Now, again, there's going to be 20,000, so it's going to just kind of flood my screen here, and it will stop after 1,000. R says, you know what, that's too many numbers, but we can see that it has pulled out kind of all of these ages here. If we wanted to extract some of the rows, we could give it a series of numbers. So here 1:10 in R is shorthand for 1 through 10, or 4:8 is the numbers 4 through 8. And so let me just kind of show the first 6 rows of CDC, and if I wanted to just pull out rows 3, 4, and 5, I could say 3 through 5, comma. You have to put in the comma because the numbers before the comma indicate the rows you want, and numbers after the comma indicate which columns you want. If I leave it blank, R will pull out all of the columns. So here, this will pull all the columns from rows 3, 4, and 5. If I do something like 1 through 3 here, this would pull out all the rows 3, 4, and 5, and the columns 1, 2, and 3, which will be general health, exercise any, and health plan for those 3 rows, for rows 3, 4, and 5. And so we can get kind of like a mini slice of our general table that's much, much bigger, of 20,000. We've already kind of messed around with this, where if you use the $, it will pull out that column. And if you wanted to, again, let's just take a look at the first few. If I did CDC $weight, this would be all 20,000. But I could just say, you know what, I want, because CDC $weight just says I only want the weight column, and I can say I want the 4th entry in the weight column. And if I do CDC $weight 4, $weight square bracket 4, this will pull out the 4th entry in this weight column, which is 132. Okay, and likewise, you can give it a range, and it will pull those things out. We can also use logical operators, comparison operators, that will say, which values in the gender column are equal to M. So CDC $gender will be this column, and here I'm going to just pull the first 6, and we will see that it's just M, F, 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 things like that. And I can say which ones are equal to M. Okay, and so here it will say true for the first one, and everything else is false. And if I did it for the entire thing, it would give me not just 6 true or false values, but it would give me 20,000 true or false values. And of course, it's going to flood the screen, and it'll just print out the first 1,000. But we can see, which of these are true or false. Okay. We can also do something similar with numeric variables. And we can do CDC $age, and we can say, okay, of these, so let's just take a look at here, let me just do the first 6 rows here. So of age, let me just do CDC $age, and we'll just get the first 6 rows of CDC $age, which will correspond to these ones, 77, 33, 49, and I can just say of these, which ones are greater than 50, okay? And so 77 is greater than 50, so it says true. 33, 49, and 42 are not, so those three get false, and the next two get true, because they are both 55 and 55 are greater than 50, okay? So this applies a condition, and it will say true or false, okay? And so now I can subset based on those conditions. So here, if I want to just say which ones are males, okay, I can say create a new object called mData as a place to store the output of this command, which is called subset. Subset says take the data table, the current data table CDC, and use this condition. Wherever this thing is true, pull out those rows. So we're going to say CDC $gender, and we want where this thing is equal to M. So this means whenever the row has this column CDC $gender equal to M, take that row and store it, and we're going to store it inside mData. So I will do that. We see mData has 9,569 observations, which makes sense because when I created table on CDC $gender, we saw that 9,569 are males. And so let's just take a look at the first few rows of mData, and we can see that indeed all of these are male, and we can see that we pulled out rows 1, 7, 8, 10, 11, and 12. So these are the first 6 rows, but they correspond in the original table to these rows, and so these are the males that we have extracted out of the original data table. You can give it multiple subsetting conditions, and you can say I want people who are male and their age is over 30, okay, and we can store that result into M and over 30 as our object, okay. You can also give it the OR operator, and the OR is an inclusive OR, meaning this will pull out everybody who is male, everybody who is over 30, or both, okay. So it will pull out males who are over and under 30, and this one will pull out everybody over 30, including both males and females. So it'll get males who are under 30, males who are over 30, and females who are over 30. Okay, and that will go into this one. Whereas this one will only pull out males who are over 30. So let me just kind of do, well, you can retype this command in here. Okay. All right, so with the quantitative data, we can create additional plots, and so we would do box plot CDC $height and summary CDC $height. Okay, and this, so if I do CDC, oops, I want box plot. Okay, this will create a box plot right over here, and this is what it looks like. So this is the third quartile, and the median, and the first quartile. Sometimes with box plots, I like to use the option horizontal equals true. And in my opinion, these are a little bit easier to read, especially when they're wider. Okay, and so here I can see that the third quartile is around 70, and the median is somewhere around 67-ish, I don't know, and the first quartile looks to be around 64. Let's just do summary on CDC $height and see how. So yeah, 64, 67, and 70, those indeed are our first, second, and third quartiles. Okay, the largest max is 93, and the minimum was 48, which are down here, and these are all considered outliers, and these are considered outliers. Okay, we don't get to see where the fences are. I mean, we don't it doesn't list off the fences here for in the summary, but we could calculate the fence, right? So our IQR is 70 minus 64, 6, and we would do 6 times 1.5 is 9, and so my lower fence would be at 64 minus 9, and then my upper fence is Q3 plus 1.5 times the IQR, so 1.5 times the IQR is 9, so my lower fence is at 55, which is right there, and my upper fence is at 79, okay, right there. And so indeed the lines extend to the lower fence and the upper fence, and anything beyond that is considered an outlier. So the summary doesn't provide where the upper and lower fences are, but we could calculate them ourselves, okay? If we recall that the lower fence is Q1 minus 1.5 times the IQR, and Q3 is, the upper fence is Q3 plus 1.5 times the IQR, we can see that the box plot indeed draws to the fences and makes everything else outside the fences a circle to indicate that they are outliers. We can create side-by-side box plots by saying, you know what, we want to create a box plot for height, but we want to separate them as based on gender. So we would do box plot CDC height tilde CDC $ gender, and so this will draw side-by-side box plots, okay, and here they are vertical again. And so what I'm going to do is I'm going to flip them over on their side by doing horizontal, whoops, equals true. And so here they are. And so now we can see here is the box plot for males, and for females up here. We can see for males the median is 70, Q1 looks to be 68, and Q3 looks to be about 72, with the lower fence at, that looks to be 62-ish, and the upper fence looks to be 78-ish, something around there. And for females, the median looks to be around 64, I'm not 100% sure, and we can kind of eyeball where these other values are as well. And we got the maximum and the minimum and things of that nature also plotted in the box plot. Okay, and then if we wanted to, we could create a variable called BMI, which is based on this formula, and we would take the weight divided by the height squared multiplied by 703, and this would take the entire weight column, CDC $ weight, divide that by the entire height column squared, and it does element-wise operations. Okay, so meaning here it would take each weight, for this weight 175, and then it would divide it by 70 squared. Okay, and then here it would do 194 divided by 71 squared, and 170 divided by 67 squared. And it would do this for every person in the operation, and we would multiply that. And so to do this, I will just do BMI is going to be CDC, I got to do CDC $ weight, I'm sorry, height divided by CDC $. Oh, wait, no, I'm sorry, it's weight divided by height squared. Weight divided by height squared multiplied by 703. And then we will create a box plot of BMI as a function of CDC general health and let's do again horizontal equals true. We'll click zoom. So here we can see people in excellent health, and as those in excellent health, the median BMI is somewhere around maybe 24, and as the health kind of declines a tiny bit, very good, good, fair, and poor, we can see that the BMI tends to increase, all right? And then when we look at the Q3, what's the 75th percentile, we can see that there's definitely a trending increase, right? And so on for both the first quartile and the third quartile. They tend to increase, and increase of BMI seems to be associated with people in poor health overall. Although, you know, for poor health, we do see the kind of the largest range as far as low to high, and so probably people in poor health, you kind of have the extremes of people who are much overweight, and people who are severely underweight would be are most likely to be in poor health, while those two who are in excellent health will tend to have kind of a smaller range of BMI values. And they're all self-reported as well, so, you know, but, well, maybe they're not self-reported, but I believe they are, and so that's what we have. And lastly, we can also create histograms. So we will do histograms of CDC $age, and we can see kind of the low end to the high end, and so most of the people are kind of in this, you know, 30s to 50 range, but, you know, as there seems to be quite a few, and as the age increases more and more, we have fewer and fewer people in our survey. We can also create a histogram for BMI, and it looks like this, and if we want finer detail, we can increase the number of bins or breaks, and we can just say, like, oops, breaks equals 50, and so that kind of makes gives us a lot more bins, and we can kind of see the right skewed nature of BMI, where most people are in this 20 to 30 range, but yes, we have people who have BMIs over 40, BMIs over 50, okay, and we also have some people with BMIs under 15, but generally it appears to be right skewed. Okay, so those are all kind of different things. All right, so here it says make a scatterplot, and we never actually covered making a scatterplot, but that's easy to do. All you have to do is you do plot, and you put in your two variables. So you do something like CDC height and CDC $weight. That would put height on the horizontal axis and weight on the vertical axis, and this is kind of the giant plot we get. There's a few options. You can change the plotting character to something like 19, which I think is dots. Okay, well, I don't know if that's any better, but you know, you can change the plotting character that is being plotted. Maybe the default circles are fine. Okay, and it says, so here it says do weight versus desired weight, and you can create a plot there, and it says describe the relationship between those two. Here we can do one for desired weight and weight, and we're going to create a new variable called wdiff. Okay, you'll do that in a similar way to the way we created BMI. And it says what type of data is wdiff. If an observation of wdiff is 0, what does that say about the person's weight and their desired weight? What if it's positive or negative? What does that mean? Questions like that. And it says use numeric summaries and a side-by-side box plot for the see if there's a difference in this value W diff, weight difference, for males and females and things of that nature. It says find the mean and standard deviation of W diff and determine what proportion of weights are within one standard deviation of the mean. Okay, so this one is probably, I don't know if it's the most challenging one, but what you want to do is you want to find out exactly, so you've got some kind of condition, right? So here we created the variable BMI, but we could also ask, let me just kind of explain the idea here, is if I do CDC $ height, I can ask for what is the standard deviation of CDC $ height, and it tells me it's 4.12, and I can ask what's the mean of CDC $ height, okay, and the mean is 67.1829. So my higher bound, or my lower bound, will be basically 67.1829 minus 4.125954, okay, and so I would get a lower bound of 63.05695. I can also just compute this directly just by saying what's the mean of CDC $ height, subtract off the standard deviation of CDC $ height, okay, and my lower bound is that, okay, and if I want to go down 2 standard deviations, I can do that also. I can just do 2, and my lower bound would now be 58.93. You do the same thing for the upper end, and then what you would then do is you would ask for, here I'll say above, we'll create something called above the lower bound, and this is going to be a comparison. We're going to say how many of CDC $ height is greater than my lower bound, okay? And what this will do, if I just ask for these values, we're going to ask for what are the first 6 values here. This is just going to be a vector of trues and falses, okay? And so I can then do a table on this thing, and here it says, okay, 19,890 are above the lower bound, 110 are below the lower bound. So that can tell me, okay, well, 19,890 divided by 20,000, and here it says 99.45% are above the lower bound. You can do something similar, and you would have 2 conditions here, how many are above and how many are below. So I'll leave that to you to figure out, and you can kind of create a table to figure out how that works, right? Or you can subset it, okay? Another option is to do subset, and you can do subset CDC, where CDC $ height is greater than the lower bound, and we'll just say above the lower bound, okay? And then we can ask for the dimensions of above the lower bound, and this will also say 19,890. And so, with subset, you can put in multiple things. You can also put in multiple conditions inside here. Well, anyway, that should be enough help to get you through this lab. So good luck. Oh, and of course, please render everything in your R Markdown file. So you will fill this out and knit it to a Word document, and make sure you include your plots. Okay, and of course and for the assignment, you are just responsible for answering the questions in the On Your Own section.